Alright, we're going to look at implicit functions. So if we want to differentiate, let's just say something like f of x equals x squared, something we've seen before. We know that we can use d dx of x squared, and that's just going to give us 2x. But we don't really know exactly what's going on here. We kind of just said the derivative of x squared is 2x, and we have to put that d dx in front of it. That's the operator for derivative. And so we want to just say this is not the entire story because there's something else going on here. So what we don't know is that, well, first, this thing right here is a differential, d dx. And there is a differential left over every time we differentiate any variable at all. So when we have d dx of x squared, we know the derivative of x squared is really 2x. But what happens is we have 2x multiplied by a differential, dx over dx. And what that means is we differentiated the variable x with respect to x. And we know that dx over dx is just equal to 1, and so that's why we would just say d dx of x squared is equal to 2x. Since dx over dx is equal to 1, we just don't write it. So let's look at an example. We want to find dy dx, the derivative, with respect to x. And since it's y is equal to x cubed minus 7x, that is y as a function of x. So we're going to find dy dx. So first, the derivative of y is just 1. But really, we just differentiated y with respect to x. And so our differential left over there is going to be dy dx. So that's where it comes from. Then we move on to x cubed. That's really 3x squared. And we differentiated x with respect to x. And again, 7x, the derivative is 7, and we differentiated x with respect to x. So if we simplify everything here, 1 dy dx is just dy dx, and all the dx terms go away, factors I should say, and that's how we get dy dx. The derivative of y with respect to x is 3x squared minus 7. So remember, dx is just 1. So what if we wanted to differentiate with respect to a different variable? Let's look at that same equation again. Y is equal to x cubed minus 7x. But we want to find dy dt. So we're differentiating y with respect to t. So we'll have 1, derivative of y. But in this case, we differentiated y with respect to t. Then we have x cubed becomes 3x squared. In this case, we differentiated x with respect to t. So our differential is dx dt. Can't cancel that. Same thing for negative 7x. The derivative of 7x is 7. But the differential left over is dx dt. And so to simplify this, all we can do is maybe factor out that dx dt. We can't simplify it by canceling. So here's our solution. All right, differentiate with respect to z. So we'll start on the left-hand side. Y cubed is going to become 3y squared. We differentiated y with respect to z. 2 pi z becomes just 2 pi, and that's dz dz. Z to the 4 is 4z cubed dz dz. And then y to the 6 becomes 6y to the 5. Here we differentiated y with respect to z, so that dy dz is the last differential there. So the dz dz's are going to go away, but dy dz is stuck. And it was asking for the derivative dy dz, so we can just get that by itself. all of our rules that we've seen, so the chain rule, product rule, quotient rule, anything, they're all going to hold. So here we want to find dy dx. If we're given x squared y cubed minus sine y squared is equal to 3. So that first term we're going to have to use a product rule. So the derivative of x squared times y cubed plus x squared times the derivative of y cubed. Second term is going to be a chain rule. So we're going to have the derivative of sine of y squared times the derivative of the inside, which derivative of y squared is equal to the derivative of 3. So notice that in that first term, we're differentiating x with respect to x. So we get dx dx. Second term, y. Here we have negative cosine of y squared times the derivative of y squared, which is 2y, dy dx. And on the right, we get a 0. So we're going to get rid of all the dx dx factors. And we're going to group together the dy dx terms and get everything else to the other side. Now we're going to factor out that dy dx and divide, and there's our solution.